lecture in which we're going to begin with 2D random walks. And before going into 2D random walks, I just want to go back to our discussion, and I think I had forgotten you to show how we can fit the normal distribution. I'm just gonna quickly browse through the program for that. So imagine you want to find out whether a given set of points, in this case the black points, they fit to a normal distribution. Well, how to go about doing that? We know that a normal distribution has this particular form. So the first thing we will do is create a function which will be the type of function that we're trying to fit. Alright. So it will take as an input x, it will take two parameters a and b. So the whole purpose of the fitting is to find out the appropriate parameters which will minimize the error between the fit and the raw data. Alright, so then this is the data we had from the histogram x values and y values. So x values and y values is what we have. Then we call the function curve fit, which is inside scipy.optimize. We pass the function handle, which will do the function evaluations. We will pass the data, that is the x values and y values. The output is the set of parameters in the fitting function. The second output we don't worry about. Alright, once we have that, we can use the same function, but now we pass the output of the curve fit function as the two parameters. So over here I'm assigning a as the output 0 of the output of the curve fit function, while I'm assigning b as the output of the curve fit, the second value of the output. So once I do that, I plot it and I give it a label, and I also plot the raw data. And after a lot of iterations, or when you move ahead in time significantly, you will see that the distribution of locations does satisfy the normal distribution. Okay, there's something which I said I would discuss in the last class, but then I forgot about it. But anyway, it's not that difficult. It is there in the HTML that I've uploaded on my website, and you can download it from there. The description is also there. So now let us move on to two-dimensional random walks. So let me create a new file. All right. So what are we trying to do? So in one-dimensional random walk, we had a random walk in which we had a walker or a particle, and it would choose the step that it would take on the line. Either it would sample from a step size distribution, so p of delta x versus delta x. So it would sample from this distribution and then decide whether it has to go over here or how much it has to go over here. So now when we extend this idea to two dimensions, we obviously are dealing with a two-dimensional plane rather than a line, and we can pose certain questions. For example, what are the number of steps taken before a given random walk exits a certain diameter? So if I define this as the crossing boundary, a Lakshman Rekha if you like, so after how many steps does the particle exit? And I'm interested to find out the total or the distribution of steps. So for example, I choose particle number 0. It maybe took 25 steps. Particle 1, maybe it took less steps. Maybe it went straight ahead. Particle 2, maybe it took more steps. So once I have say 10,000 particles, I have a bunch of total steps the particle has taken. Then I can find out the histogram of this to find out the PDF of n, that is the number of steps. Alternately, I could also ask the question after, so here we are asking how many steps it took, or we could equivalently ask that at a fixed time t, what is the distribution of the locations, that is the radial distance from the origin. So if this is the origin, at a given time t, what is the distribution of locations of the particle? So I'm interested in the distance rather than the coordinates. So these are some of the questions which are quite important from various physically naturally occurring phenomena like foraging. So if you have a herd of lions and say you're in the savannah and you're hunting for food, so what do predators do? They move a large distance, then they look around, then if they find something well and good, then they know that the area is depleted in resource, then they'll make a nice jump again, and then they'll again look around. So there are these large jumps and there are the small foraging. Okay, so this foraging behavior does appear to have such a pattern, and as you will see, such kinds of patterns are common for what are called as eviphrites. Okay, but for example, if you're trying to figure out how an insect on the surface of a pond is moving, you track the insect and you will see that it has all sorts of behavior going on. But then what dictates that behavior, or what governs that motion of the insect? Is it the presence of some other insect? How does the motion get altered in the presence of other insect? How long, how many steps does it take for the insect to reach, for example, say a source of food? So these are some of the questions, and depending on the problem at hand, it's usually how you would define the random walk. There is no universality to how you would go ahead and define the random walk. Okay, so with this background, let us begin. So we will need the opening bit of code, and I will copy it from, pardon me, I will copy it from one of the previous programs. All right, so now how do we go about this? Let us look at the simplest random walk, what is called as the Pearson walk. So Pearson walk is, you start from the origin and you have a sort of uniform, not a uniform, but you have a fixed distance that you would take. So each time a step is taken, the length of the step r is fixed, it is equal to L, but the direction can vary between 0 and 2 pi. So the direction is uniformly distributed, but the step size is fixed. So in terms of writing down the PDF of this, if it's one dimension, so you would say P of R is delta R minus L, right? So this is the delta function, and accordingly you can find the cumulative distribution of this function as well. So the cumulative, so C of R, it will be integral P of R prime dr prime, R going from 0 to infinity, or in this case 0 to R, and so this will become integral delta R prime minus L dr prime 0 to R. So now if the domain is 0 to R, right, if the domain of integration, so if L lies in 0 to R, then this integral is going to be 1. If L, it does not belong, it is outside 0 to R, then this integration will be 0. So the cumulative distribution for such a function, it will be 0 and then suddenly 1. So now if you look back and on how to sample a certain random number from a given probability density function, you would uniformly you would draw a uniform number between 0 and 1, projected on this curve and then projected back. Because it's a vertical line, all your samples will fall at r equal to L. And obviously these are properties of the Dirac delta function. Okay. So I've used the important property that integral f of x prime delta x prime minus a dx prime from L1 to L2, lower limit and upper limit, or L1 to U1. This is going to be f of a. If a lies between L1 and L2. If a does not lie in the domain, then it will be 0. So these are just some properties of the delta function. So now this is okay. I mean, this is quite easy to implement. You can imagine you have a fixed increment r. So you're starting over here. You have a fixed increment. So your trajectory will lie somewhere on this circle at the next time instant. But as to which angle it will take, that depends on the sampled value between 0 and 2 pi. Okay, so if it's 0, it will move over here. If it's pi, it will move over here. If it's pi by 4, it will go over here, and so on. And after you reach this point, you will again do this. So if it's after reaching this point, if it is pi by 2, it will go something like this. Okay, so let's try to implement this. So first things first, we can borrow certain things from the previous lecture. So let me open that file as well. So we will use the uniform distribution code. So here we will say get angle, and it will go from 0 to 2 pi. And so what is the workflow that we're looking over here? So the workflow will be, we initialize the vector, that is x naught. So this is at t equal to 0. So this is time, this is x, this is y. All right. Then we want to find an increment. So we know that in this case the step is fixed, so it is L. We will sample theta, and we will sample some theta. Okay, so theta belongs to a uniform distribution between 0 and 2 pi. Now based on this, the delta x will be L cos theta and delta y will be L sin theta. So at this, so at the first step, so instead of calling it delta t, I'll just call it 1. It will be some delta x1, delta y1. Then at time 2, it will be delta x2, delta y2, and so on. For n, it will be delta xn, delta yn. So at the end of this, the trajectory will be the cumulative sum up until that point. So suppose I want to find out the trajectory up until 3. So it will be simply 0 plus delta x1 plus delta x2 plus delta x3. This will be the x coordinate. The y coordinate will be 0 plus delta y1 plus delta y2 plus delta y3. So if I sort of plot the cumulative sum all the way, I should be able to find out the trajectory. Well, let's find out. So over here, what is n? It is not the particle number. It is the time instances that we want. Okay. Unlike the previous problem where n was the number of particles that we were initializing, here we are fixing our attention on one particle, finding out all the mutually independent steps that it will take, and then we make a cumulative sum. All right. So n over here is representing the time steps. Okay. So let me just put a comment. All right. Diff get stride n. It should simply return np dot ones, and the size will be n comma, right? So it has to just return a bunch of ones. All right, so these are the two functions that we want. Well, now I can focus on one particle. So I will say how many time steps do we want? So let's say we want 200 time steps, right? So then what do we do? For I in np.a range 0 to n, now we have to define the initial value or the initial location. So x naught comma y naught equal to 0 comma 0. That's fine. Now what we will do is we will create the increment array. So if we have 200 steps, what will be, so let us make the increment array to look something like this. Let this be the increment array. All right. So the increment array we will say as, just let's call it x equal to np dot zeros. So now it has to be of 2 rows and n columns. All right. Oops. So yeah. So we have created x which has 2 rows and n columns. So and obviously we are initializing with 0. So x naught y naught, it doesn't make sense. So now we will do for I in np.arange 1 to n, because the first point is already the origin, so we don't need to worry about that. Now what we will do is we will write down the logic. So x, so for the ith column, the first, let me just do this. So this will be delta x, so this has to be 0 and this has to be delta y. So basically if I'm over here, the 0th row, ith column, this will be that particular increment and this will be this particular increment. So the increment in y will have a row number of 1, whereas the increment in x will have a row number of 0. Now delta x will be L times cos of theta delta, while delta x and delta y will be L times np dot sine of theta. But now what is L and what is theta? So L will be, in fact we don't even need to run this in a loop. We don't even need to run this in a loop. We can simply pass n and obtain all the steps that we need. Oh, fine. And then we can augment it with zeros. Okay, so well, because I've written it so far, let me just, so we'll just call one angle and one stride at a given time. L equal to get stride one element and theta equal to get angle one element. So I'm not vectorizing the code. I am asking it for each time step, give me one stride and one length. And obviously the stride will be 1 and the angle will also be 1. So I'm not vectorizing anything. So let me run this and okay, there is an error. Sorry. Okay. So now let me show you. So after this, we have generated a series of x and y increments. So let me do the following. Let me do a cumulative sum. So x traj or x increments, we will say x 0 comma all, and y increments will be x 1 comma all right. Now we must do a cumulative sum. So x traj will be np dot cum sum x increment and y traj will be np dot cum sum of y increment. All right. So far so good. Now we will plot x and y, and that should give us the trajectory for a single particle. So plt dot plot x traj comma y traj. Okay, so this is how the trajectory looks like. It started over here and it's doing this random walk. Okay, so if I run this again, I will get a new random walk. So let me, because it's gonna sample a new variable again. All right, so let me do that. Great. So it's going in the other direction. So let us now wrap this entire program so that we can run it for a few more particles. So let me copy this. Let me go over here and let me let me do it for more particles. So let me write np equal to say 10, and over here I will write for j in np.arrange 1 to np. So I'll do the whole initialization for each particle and eventually I'll do the plot. So now let me run this and see what happens. This has to be common. So great, we have 10 trajectories using the Pearson walk. But now I have this data, but now what I really want to know is I don't want to know the trajectory. I just want to know what radial location the particles are at the end of 200 steps. So how do I go about doing that? I don't want to find the trajectories. I don't want all this. So that's quite easy. So in fact, let me preserve this bit of program. Let me go over here. And so we still have this. We still have number of particles. And what we will do is we will wrap all of this. In fact, we don't need a cum sum because cum sum is required to find out the entire trajectory. We just need a sum. And the sum will give me the final point. Okay, the sum will give me the final point. Once I have this, I will find out the R origin is equal to x traj square plus y traj square, and I will take a square root of that. That is, it is the distance from the origin, and I don't need to plot it. So what I have over here is a function, is a neat function which will give me the final distance from the origin. So I will cut this. I don't need all that. I will define a function. So I will define get final location, and I will pass n, that is the total number of time steps. So over here I have to do the same declarations and eventually I must return R origin. Okay, so it is abstracting that bit of code that you have to find the trajectory blah blah blah, but no, I don't want to know all that. I just want the final distance. So I will simply go over here and I will simply call the final get final location. So I will say get final location lock, and I will pass n, that is for a large number of particles np. I will pass that I want to know the final location for n number of steps, that is 200 number of steps. I will assign it to an array R, right? And I will say R, that is the final location, is equal to np dot zeros, and it will be of size, yeah, n rows, and it's just n rows, it's a vector. Okay, so let me run this. Okay, it seems to have run. So let me print out R. Sorry, it has to be np. It doesn't have to be n. It obviously has to be np. It has to be number of particles. Okay, great. So let me print out R. So these are the distances at the end of 200 steps. Why is this has to be from 0? Okay. So these are the distances at the end of 200 time steps. If I increase the number of time steps, I will get more distance from the origin. Let me see. So over here you see a bunch of 15 7s 24s, but when I make 500 steps I should get a larger distance. Okay, so now we are interested to find out the distribution, right? The distribution of the r. So let me make it 10,000. Let me make this as 200. So 10,000 particles, I should be able to then, it will take a while to run because the code isn't vectorized. And in fact, I will ask you to vectorize it as a part of your home task. It's not going to be an assignment, but you should go ahead and try to do that. I'll tell you what the logic will be. Well, the program has run by now. Let me just, it's a big array. So let me just plot it. So uh, PL, so bins counts nothing equal to plt.hist, and I will plot the histogram of R. Bins equal to, let's say, 40 bins, density equal to true. So it gives me this kind of a distribution. Okay, if I want a better fit to this, I'll probably use more number of particles, and it will show this kind of distribution, and it will be more illustrative when we do this in a log scale. On the x-axis, if I take it in a log, it will show some kind of a power law. This decaying tail may show some kind of a power law, and that's for you to explore once you start learning about random walks and the distributions that you get from multidimensional random walks. But this gives a very clear-cut overview of what is going on, right? And okay, so how do you go about vectorizing this? It's quite easy. Well, we have created the get angle and get stride function. So I'll just give an outline. I'm not going to implement this. So because you know the number of steps, so then you will ask for get angle for n values. So you will get a bunch of angles ranging from 0 to pi. Okay, you have a bunch of angles, you have a bunch of lengths, and then using the formula delta x equal to L cos theta, delta y equal to L sin theta, you will have a bunch of increments. Okay, so then you augment this array with a 0, and then you simply find the sum. So in case you're just trying to find the sum, you don't even need to augment the array with 0. You just find the sum of these matrices. Okay, and that's it. And let me just for completeness show you how I would do that. So let me say s1 equal to get angles, get angle. Let me just do it for 10. Okay, and s2 equal to get length or get stride 10, right? So let me print those. So these are the angles and these are the strides. Then you will say dx equal to s2 times np dot cos of s1, dy equal to s2 times np dot sine of s1, and so then you will have dx and dy, and then you will say location x equal to np dot sum dx, and location y will be np dot sum of dy, and that's it. I mean, with the help of this you will have the final location. Okay, so you don't need to run all those things in a loop. Okay, and in fact I'll do the modification once we go to the Levy walk, the Cauchy distribution, but for now it gives a very clear overview of how you go about this. It's just you can avoid this loop altogether. Well, I'll let you do that. Well, now that we have looked at a bounded distribution, we can turn our attention to a Levy walk. Well, let me reuse this program. So now instead of having a unit length as the stride, let us do it for a Cauchy distribution. So Cauchy distribution looks something like this. it is usually 1 upon pi times 1 plus x square, and this is for one dimension. So this is the p of x for a Cauchy distribution, and it's a symmetric distribution about the origin. Okay, about the origin, it's a symmetric distribution. But now I am interested in the absolute value. So we are more bothered with sampling the radial stride in a random walk using a Cauchy distribution. So for that, the distribution is actually 1 over pi square r times 1 plus r square. And the reason is because once you try to find the cumulative of a step size distribution in two dimension, it will not be simply integral p of x prime dx prime, but rather it will be integral p of r prime 2 pi r prime dr prime if everything is symmetric, because it needs to find the area. So this is the area in 1D, this is the area in 2D. So then what is the cumulative of r? It will be integral 1 by pi square r prime 1 plus r prime square 2 pi r prime dr prime. So this pi cancels out, so it's r going from 0 to r prime going from 0 to r. So this becomes 2 by pi integral, so this r prime cancels out, dr prime by 1 plus r prime square. So this is the same as finding out a, or a sampling a variable from the Cauchy distribution in one dimension. Okay, so that gives us something to work around with. So instead of having np dot ones, we can now have np dot random dot Cauchy. So let us look at what the syntax for standard Cauchy is. So mode 0, no problem, and this is the distribution. Standard Cauchy is x not equal to 0 and gamma equal to 1, yeah, no problem. So we need to just give the size. All right, great. So size equal to n comma, and let's save it. So now, but wait, so the Cauchy distribution will give you negative values as well, so we need to or return the absolute value of this. All right, so we have returned the absolute value. Well, let's run this, let's see what happens. So boom, now we have what is a Levy walk. So it starts over here, it makes huge jumps, then wanders around, his huge jump, wanders around, huge jump, wanders around, huge jump, wanders around, and things like that. So it's a classic foraging behavior. In fact, let me now run this program for np number of particles. So let me grab hold of this program. So the beauty is we can reuse program. I mean, you don't need to be rigid about it. We just need to change how we sample the distribution. Okay, so now let me run this. So these are, so let me make the aspect ratio correct. So all right, so one of the distributions really flew off. So the thing is Cauchy distribution. Okay, so the Cauchy distribution has that kind of a fat tail that we had discussed in the previous lecture, corresponding to a Levy stable distribution or a Pareto distribution. So it does have a tail in which there will be a small yet finite probability to get high jumps, so high values of delta x or delta r in this case. Okay, so there will be a chance to get that. In fact, let me just show you, let me just plot the distribution function. So r equal to np dot linspace 0 to 10, and f will be 1 over pi square times r times 1 plus r square, and then we'll do plt dot plot r comma f. Okay, so it looks something like this. So the values are not 0 over here. They are small values, but they are not 0. So let me make it a log. Because it's small probability, but not 0. So you will more often than not sample things which are in the higher probability zone. So you will sample small steps, but every now and then you will sample that large step, and that gives rise to this kind of a walk. Okay, let me run it one more time. So each time you do it, you will get a random walk. Okay, so now let me reuse one of our previous programs to find out the distribution of length for such a random walk. Let me copy this. Let me paste this. So now what I'll do is I'll make this get final location vectorized. All right, I'll make it vectorized. But before that, let me just change the get stride function. I must replace it by this. All right, great. So I will remove all this. I will remove this. I will say dx is n comma 1. I will say dy is also this, and I will, instead of calling it in a loop, I will get ln theta. I will remove the indentation. Once I have ln theta, then so this is just initialization. So then dx, well, you don't really need to initialize this. You don't need to really initialize this. It's sometimes good to initialize. Okay, so then dx. So instead of getting only one stride, we'll get n strides. And dx will be L times, np dot cos of theta. Dy will be L times np dot sine of theta. We don't need this. We don't need any of this. Alright, x trajectory will be simply the sum of all increments, and the y trajectory will be simply the sum of all increments in the y direction. And yes, that's it. This is the entire function. We have got it down from bunch of lines to only 5 lines. Great. So let me run this, and oops, there is an error. Get final location. So okay, what is the problem? Let us see what is the problem. So our origin. So let us print out. So it's a bunch of okay. The issue is this has to be white trash. Okay. I don't know why I did that. Okay. So it's running the program for a bunch of particles. Let it run. It's already run. Oh. No. Okay. So it's already run. We need to do the PDF. So let me copy this just to find out the PDF. Okay. So obviously there are some values over here, but most of them are still centered around the origin. In fact, let me decide what the bin locations will be. So I will call it as bin space equal to np dot linspace, and let it go from say 0 to 100. Yeah. So let us run this. Okay, so the distribution looks something like this. In fact, we can increase it to 500. Let's see what we have. So we have something like this. So it's a much fatter tail than before compared to the distribution over here. So it decays down much faster, but over here it tends to decay much slower. So at a given point in time, there are majority of the particles over here. So the time we took was for 200 time steps. It is peaking around 100. What was the peak over here? It was something around 10. Okay. So the a larger peak is indicative of larger steps taken because of the Cauchy distribution, and the distribution appears to be tailing off very slowly, and these are all highlights of the Levy walk. So these distributions are usually a power law distributions. Okay, so there are particles which have traveled such a large distances. They are not large in number, but regardless, they are there. Okay, so I'd like to conclude this particular week over here, and a lot of things we have seen. And once you start doing a course on probability and statistics, I really hope you will find all these tools that we have discussed immensely useful, and I hope you will make the best use of it. With this, I'll see you again next week. Have a good week. Bye.